Hey, Colin.
What physics do you have for us today?
Hey Maria, hey Ryan. I wanted to talk to the two of you about potential energy curves while I'm away at the conference this week. Can you tell me a little bit about how you think about a curve like the one on the screen, what that means to you?
Well, what it looks like to me is that you're going to have a particle that's moving in one dimension, right? And it's going to experience different forces at different points. And its motion is going to be affected by the potential energy curve.
So we have this potential energy curve, and we can actually think of it as analogous to a roller coaster, right? Not
Sure.
not in two dimensions, because a roller coaster is actually going up and down, but its x motion is going to be the same as if it were sort of a 1D roller coaster.
Okay, so let's say that we put a particle at the origin. What's the motion of that particle going to look like?
So if you put a particle at the origin, it should fall down the slope. And because the beginning potential energy is greater than the potential energy at the next little bump, it should have enough energy to roll over that bump and get past it.
Indeed, and so again, it's only in one dimension, so let's see what it looks like.
Right. So we only see the forces acting in the x direction, since, like you said, it's a one-dimensional system.
Okay, and so you just reminded me that force is the negative derivative of potential energy, right?
That's right.
Ah, yeah, I remember that from class.
So, given some potential, we can easily find the forces that are acting on the particle just by taking the derivative.
And so when we look at the graph, we can see that at the beginning, the force is to the right, then to the left, then to the right.
And this makes sense, right? Because if you have a positive slope, that means that you're going to be moving up a hill, and you're going to have forces pushing you back down. If you have a negative slope, you're going to be moving down a hill, and you're going to have forces that are pushing you down that hill.
It's still just moving in a line. Awesome.
Okay, so how about the equilibrium points for that particle? How would you find those points?
My guess would be that equilibrium points should be at A and C. That's what I'm gambling.
That makes sense. We have local min and max, and so, but which one's going to be which? It's analogous to a roller coaster, and so I'm guessing in the little valley created by the concave up piece that it's going to be a stable equilibrium, because if you moved like the roller coaster a little bit away from the point at A, then it would come back.
Sure. So it acts a little bit like a spring. If you have a little mass on a spring, you give it a little push, it's just going to bounce back to where its initial starting position was.
All right, because of the slopes around A, the force is always pointing back towards A.
Exactly.
All right.
But what about at point C? If you give it a little push at point C, it would just go down the hill.
Ooh, yeah, so that must be unstable, because it's not getting back there if it moves away from there. Whee, goodbye.
I wonder, is there a way we could find this mathematically, though?
Of course. So we have local mins and maxes, so that means our derivative is going to be 0, or our slope is going to be 0.
But
Yay!
how does the math tell us which one is the stable and which one is unstable?
Let's see. Oh, this is when we look at the second derivative.
What? Two derivatives? Okay.
Again, because this is analogous to like a roller coaster, so when the second derivative is positive, so when we have a concave up section, then
You're going to have stable equilibrium points.
Yeah.
So what we can do then is we can find what points are the local maxima and minima, and when we have that, we then test them for whether they are maxima or minima, and using the second derivative, and that tells us whether it's a stable or unstable equilibrium point.
Exactly. Right, so we have these regions with a second derivative greater than 0, and we have the local min, so that is our stable equilibrium, and then here is where the second derivative is less than 0, and so that local max is our unstable equilibrium point.
What about the velocity of the particle?
If we want to find the velocity of the particle, then we can, think about it qualitatively. And if you drop it down that hill, the velocity is going to be greatest at point A, when it's, just had a force acting upon it for a little bit. But then at point C, it's going to be a little bit lower, because the force was just pushing it back down, but it managed to climb up against all odds.
Yeah, and so we have, I think what you're getting at is that we have conservation of energy.
Correct.
So potential energy is going to get converted into kinetic energy. And that means we would have to be given a total energy.
Right, which would line up with where the particle starts.
Indeed. So it starts at the origin, and then at points A and C, there's our potential energy, and then the rest is kinetic. And so you're right, it's faster at point A and slower at
Cool.
point C.
So can we actually find this quantitatively using math?
Oh, yeah. So, conservation of energy. Do you remember what the formula is?
Come on, I remember conservation of energy. That's key. Conservation of energy says that the kinetic energy, which is 1/2 mv squared, plus the potential energy, which is the potential function that we're given, u of x.
Perfect. And so then how do we find velocity?
Velocity, we would just solve for v, and we'd have v as a function of x is equal to the square root of twice the difference between the total energy and the potential energy divided by the mass of the particle.
Awesome. Heck yeah.
That's what's up.
Let's reduce the energy of the particle now. Let's look at a different situation where the amount of energy that we have is lower, like you see on the screen here. What's going to happen now for the velocity at points A and C?
Oh. Uh-oh.
We're lowering the energy a lot. So that means that the particle is going to be starting at a different point, right?
Yeah, because so the lowering the energy sort of cut out part of this graph, so you can't have more energy than the total energy, and so I think weird things are going to happen.
It looks like the particle should start a little bit to the left of A, and it will only be able to get to point B, because after that, it doesn't, like you said, energy has to be conserved, and it doesn't have enough energy to get past point B.
Yeah, and so, yeah, C can't happen, and that makes sense. So potential energy and kinetic energy at point A. It's going slower than it was before, and so, yeah, it just can't get to C because it wants more potential energy than it can have. But if we look at that point, if you are given this U value, can you then just have negative kinetic energy?
That's weird. What about, how does it work out mathematically? Maybe that will shed some light on it.
And so you have the potential energy greater than the energy, and so you have an imaginary velocity?
Right, because then if you have the square of an imaginary number, it's negative. So you have negative kinetic energy. So this makes sense because this can't actually happen, right? You can't have a negative velocity. Negative velocity is imaginary. So this makes sense, and it basically just says that you can't go past point B.
So what you've run into there with the negative is a disallowed region for the particle. The particle just can't get there. There's some kind of barrier in the way. In this case, there's too much potential energy that it would have to have, and it runs out of kinetic energy. These are called classical turning points, where the particle reaches a certain place and then turns around and head back the other way.
So why is it called a classical turning point?
They're called classical turning points because quantum physics uses turning points a little bit differently. In classical physics, you can never find anything past its turning point. In quantum physics, you actually can. That's where quantum tunneling comes from. A particle can disappear from one side of a barrier and appear on the other side of a barrier, even though it couldn't, in classical physics, have gotten over that barrier. It just doesn't have enough energy. In quantum physics, it can be found on the other side. Well, it's great working with you guys, and be glad to see you when I get back.
See you soon, Colin.